All right, testing 1 2, testing 1 2 3. All right, we're back. Again, this is EJ Daigle, Dunwoody College Technology. I'm going to do a little lesson here on the Siemens S7 1200 PLC using the TIA Portal software, and this particular lesson will be on math and compare instructions. Typically, when I start with math and compare instructions, I want to do just a real quick review of number systems and data types. What are number systems and data types? Not all of these do the PLC necessarily care about. So like your natural numbers, this would be 0, 1, 2, 3. We call the natural numbers our counting numbers. They're only positive numbers. Pretend you're counting with your fingers. 0, 1, 2, 3, 4, 5. This is how we learned to count as a kid. Those are the natural numbers. They go from 0 to infinity, but they always start at 0 and they always go 1, 2, 3, 4, 5, 6, 7, 8, so on and so forth. Integers, this is one of our common numbers that we'll use in the world of PLCs, and we actually call them integers. These are, negative numbers. So you could have negative 32 would be an integer, 0 would be an integer, 1, 2, 3. These are all integers, right? But so is, 32,000. Or 320,000 may be an integer as well. 32. I'm going to be careful on using 320,000 because depending on your data type, they may not work. Negative 16, 3, 16. Basically, the integers, these are your whole numbers. These are your whole numbers, both negative and positive. So what's different? Natural numbers are whole numbers as well, but they're only in the positive direction, from 0 to the positive direction. Integers, in the real world of mathematics, they go from negative infinity to positive infinity, but they're only the whole numbers. That's all they are. The rational numbers are the things that we can write as ratios. So any of the integers, this is one of the things when you see how these are drawn in, all of the natural numbers are also integers. All of the rational numbers are also integers. Well, how is that possible? Well, the number 2 as an example can be written as a ratio, 2/1, right? That's a rational number, and it's also the integer 2, right? But rational numbers include a lot more than that. So a number like 1/3, I can't write that as a whole number. It's equal to 0.33333333. So these are now going to include these floating point numbers, right? Things that are decimals, like 3/2. I can write that. That's 1.5, right? I can write negative. Well, here's an example too. Negative 16/1. That's a rational number, but it also can be written as an integer, right? So rational numbers, think of that word ratio. And so if it can be written as a fraction, even if it's a whole number, if it can be written as a fraction, then it is also a rational number as well, okay? 5/3, 1/8, there's lots of different examples. And they don't have to be these real simple numbers from 0 to 1, right? You could have 365/7. That would be a rational number as well. And so let's get into the irrational numbers for a second here, because we kind of got this big bubble of rationals and irrationals, right? The irrationals are the ones that they're not as simple as these rationals. I can't just write them as a pure ratio. So we take the number, pi, which is approximately equal to 3.14, and we approximate it to 22/7. But this is not true. That is not pi. 22/7 is approximately pi. 3.14 is approximately pi, but as we know, this 3.14 goes on, right? 3.14159 something 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 goes on and on and on. Euler's number E, which is 2.72, and it goes blah 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 blah, goes on and on and on. So there's lots of these irrational numbers that are defined in nature that we can't define, as rational numbers. Well, all of these fit into the real numbers. And really in the world of PLCs, we only consider ourselves with the real numbers, and we can use the irrationals as well, but to be honest with you, most of what we do in the world of PLCs are going to be here. What we don't see a lot in the world of PLCs, we're not going to see the things that aren't real numbers, the imaginary numbers, the square root of -1 or something like this, the number I, we're not going to see those numbers in the world of PLCs necessarily. We'll see them in mathematics a lot, but not in the world of PLCs necessarily. Okay, so when we talk math and compare, the first thing I like to talk about is compare, because we've used this a little bit. So we've got compare instructions like equal to, not equal to, and you'll see not equal to also drawn this way, depending on what book or what platform you're working in. But when you see greater than and less than, or less than and greater than and less than, it can't be both. So that really means not equal to. Greater than or equal to, less than or equal to, greater than, less than. And then this okay, I've always liked this one. This one checks validity of the data type. So you'll see in a minute here as we work with compare instructions in the world of Siemens, we not only are comparing two numbers. So like as an example, this is a number, a tag for a number that's stored in memory location. It's a word. MW1200 is where this number is stored, and I'm comparing it to the integer 100. So you'll see not only am I looking to see if it's greater than or equal to, I'm looking to see if it's greater than or equal to the integer 100. So that's where you can see I could check validity, right? I could check validity by seeing if a number is truly what I think it is. You know, is it an integer? Is it not an integer? So on and so forth. Just there we go. Ooh, nope. Lost my computer there for a second. All right, let's hit escape here. There we go. So when we talk about these compare instructions now, in this case, I'm comparing what's in MW1200 and seeing if it's greater than or equal to the integer 100. So I plug this value in, I plug this value in, I tell it's an integer, I tell you I'm looking for greater than or equal to, and let's say the number in MW1200 was 350. Then this instruction would go true and it would turn on my output, right? Because this is greater than 100. We can also, besides comparing integers, we can compare bytes. So you can see now this is a byte. Well, what's the difference between a byte? Well, a byte is only 2 to the 8, right? So an integer is 2 to the 16. So I only can go from 0 to 255 on this guy, right? So as a byte, I'm not going to be able to put a number down here like 32,000. Up here I could put a number like 32,000, but down here I will not be able to do that. But in this case, I'm looking at the number stored in MB. That's going to be our short integer, or our byte address is what it is, MB1204, and I'm looking to see if it's equal to the number 100. If the value in MB1204 is 100 and it's equal to 100, then this output goes true and everybody's happy. Now I'm going to warn you about assigning addresses to counters, timers, different things like this. As an example, you'll see here I've got a counter, counter1 tag, and we've assigned it this memory address MB100, which is a byte, or a short integer as we also call it. It's important when I go and to do this next tag, I've got an integer 1 that I'm going to tag, that I went ahead and tagged it as MW100. And people will say, well, why'd you do that? Well, the reason why is, MB100 only takes up byte 100. So this is a byte address, and it is byte 100. So byte 100, MB100 is only going to cover that guy, right? MW100, though, however, is an integer. Okay, it's a word, or it's an integer, right? So as an integer or as a word, we know that that doesn't take up 8 bits anymore. That takes up 16 bits. So it's going to take up 2 byte addresses. So it would take up 101 and it would take up 102. So this would be MW101, would go all the way out to here, from there to there. So it's important that you're thinking about these addresses as you're building them. And then you'll see down here I said, well, I'm going to create a double here. Double that I'm calling MD103. Well, people say, well, why MD103? And then you go to MD107. You skip by 4 there. Well, the reason why I did that is MD is a double. And we know a double is 32 bits, or the equivalent of 4 byte addresses, right? So I need to have 4 of these now. So so for this one as an example, MD103, I would consume 103, 104, 105, and 106. That means the next double address, or the next address I'd have available, wouldn't even start until 107, right? I couldn't even touch 106. you can, and it won't necessarily give you an error if you do that. But what can happen is if you end up using this amount of real estate for one of them, and then all of a sudden on the next one you use this real estate and you write into this same byte, you can get some some memory overlap that can cause you some problems down the line. So my recommendation actually would even, what we're showing here is, well, if I'm counting by bytes, I'm counting by ones. If I'm counting by words, I'm counting by twos. If I'm counting by doubles, I'm counting by fours. My actual recommendation for you would be, regardless of what you're doing, is just count by fours. So I'm going to go MW100 maybe is where I start. And the next one I'll go is MW104. And regardless of what that next one is, MW108. And maybe the next one is just a byte, but I'll still go 112. And for the next one, MD, I'll still go 116. Now, what's the danger there? There really isn't any. There's plenty of memory. But what you're really saying here is you're saying when you got to MB112, you only used 112, and then you started at 116, right? So MB112 only used this, and then we didn't use the next 3 bytes, right? Is that the end of the world? No, because we didn't start here then for MD116. This is much less dangerous than we went out for here, right? This is much less dangerous leaving unused than potentially having memory overlap. So just a good rule of thumb, I just tell my students or people using the memory addresses, just count by fours. I can remember programming in BASIC on the old IBM PC platform, and when we were programming in BASIC, we would start counting by tens. So you'd have line 10, line 20, line 30, line 40, line 50. And the idea was, it wasn't that you had memory, allocation problems, but the idea was if I'm writing in BASIC and I was like, oh crud, I forgot to do something. Well, I can go back in and put a line 15 in here, right? And I still have got room to add in there. I'd say the same is true here. If I go by fours, I've still got room in here that I can use later on. But more important to me, I don't have any memory overlap potentially happening there. The in-range. In-range is a pretty cool tool here. So the in-range box instruction that you can use, again, you'll select the data type that you want to use. So in this particular case, we call it an integer. We see that we've got a counter value that we stored its current value in MW1200. And what in-range does, it says select a minimum and select a maximum. And if your counter value in val is in between the minimum and maximum, turn on the output. Turn on this Q output, whatever it is. If it's outside of 128 to 156, then don't turn on the output. So I really like, there's also an out of range instruction too, which I think is kind of silly, because if I look at in range, I can use, I can tag a bit to it that's not on or something like that, right? But this is a very valuable instruction, and it's not limited to counters. this could have easily been just an integer, the result of a math instruction. I could also change the data type, right? I could do this with a real. So I can do it with any of my normal data types that you'd see in counters, timers, integers, reals, so on and so forth. But it's really nice because I can set up what is the range, and if I'm in between those two numbers, if whatever I attach to that value is in between those two numbers, the output's going to turn on. Siemens math instructions. So just like I was showing you too in the in range there, Siemens math instructions are performed with integers, double integers, and reals. You can see how when you go to the divide block here, the auto will set up the instruction for the best data type that tries to avoid truncation. Auto works pretty good. The auto will tend to kind of over exaggerate, meaning it'll use more memory than it might need. If you're only going to be dividing small numbers, you might be able to get away with doing just integers, where the double might resort to a double integer just because it's not sure what the number value is coming in. But in this case, because it sees two integers, the auto value should say, oh, I'm expecting an integer. However, because I'm doing a divide, maybe I'm not expecting an integer. Maybe I'm expecting a real number out with a float. To avoid truncation, I'll store it as a double, right? So just know that any math instruction you do inside of Siemens, you're going to select the data type that you want to use with that instruction. So as an example here, and I actually got these two set up as autos, what I first did was I did a multiply instruction where I'm going to take the number in MW100 and multiply it by the number in MW103. These are both integers, so let's just say I've got 3 times 6, right? I'm going to store that in MD107. Now you'll see what I did here. I did the addressing kind of the way that makes sense, right? MW101 means it's going to take up 2 bytes, so I didn't start my next address till 103. I would have been just as happy as calling this MD, 105 and just counting by 4s or something. But as long as you're aware how much memory the word takes up, and you're taking that into account, that's a good thing. So 3 times 6 is going to be 18. I'm going to store 18 inside of MD107. Okay, so now 18 gets stored inside of MD107. Now I'm going to take 18 and I'm going to add, so 3 times 6 is 18. 18, I'm going to add 32 to that. So that sounds like that's going to be 50. And that's going to get stored in MD111. So it's just simple math instructions that we're pounding through these different examples. Now you'll notice this was left as auto, and it selected this double int as what it was going to use. And I think part of the reason why you see it select the double int there is notice that this is a double. So as soon as it saw a double there, it said, well, we probably need to be dealing with doubles, so let's go ahead and deal with doubles. All right, then let's talk about memory allocation. So yeah, this is a good one here. So counter, a double integer accumulation value. What I would probably want to do for that, let's say we're starting at, I'm just going to call it M100. Start at memory address 100. Because a counter value is going to, in this case, be a double integer, I'm going to start at MD100. Okay. The timer preset value, okay, that also was a double integer. How do I know that? Because it went up to 2.14 billion. Didn't go up to 4 billion, it went up to 2.14 billion. And it's also not a signed double integer, but regardless, I don't care. It's a double. So it's a double. I'm going to go MD 104. Now I'm just going to count by 4s. If I want to divide 2 real numbers, now you got to think about what kind of data does that mean. If I divide 2 real numbers can include decimal numbers, right? So like 3.5 divided by 7.2. What that means to me is I'm probably going to get a real number out. If I'm dealing with reals in, I probably want to deal with reals out. So I'm going to go to MD 108. Okay, comparing something equal to 4.5. So when you look at the compare instruction, you're going to have equal equal. On the bottom, you're going to have 4.5. Well, what this means is since this is a real, I'm expecting the part that I'm going to compare with to also be a real. So that real number right there, I'm expecting that to be a real number. I'm going to make that MD112. All right, an integer. Now here's where it gets a little tricky, right? An integer is not a double necessarily. It could be a double integer, but we're telling you it's an integer. So normally this would be an MW, and I'm going to make it a 116, regardless of it being an integer, because this double took up 112, 113, 114, 115. The next available address is 116. Now this next address, we know that this is going to be, both of these guys now are going to be doubles. Now it would be okay for me to make this next address MD118. Why? Because the integer is a word, I'm only going to take up 2 byte addresses, 116 and 117. However, I would tell you just stay away from this idea and just go ahead and make it MD120. Why? Because then there's just no possibility. What's the worst that you did? The worst that you did was you left a couple addresses, 18 and 19, open. But unless you are using a ton of memory, I just wouldn't worry about it. And then a double for the string, I'm going to do the exact same thing, MD124. So what you see in this particular address, this particular example, what you're seeing me do is I count by 4s, regardless of whether I need it or not. I count by 4s. The one example, this one, I didn't have to count by a 4 because the integer would have only taken up 2 byte addresses, and I could have started at MD118. However, I'm not even going to take a chance. What if somebody at some point decides, actually this shouldn't have been an integer, that should have been a real number, and they go ahead and change that to an MD116, and this is an MD118. Now you've got memory overlap. So by counting by 4s, you just eliminate any possibility of memory overlap in the future. So these are some of the math instructions available to you. Obviously add, subtract, multiply, divide. You've got exponents that you can do. You've got absolute value, square root, the natural logarithm. So these are 2 different ones here. and I can never remember which one. One of these is going to be like an x to the y, and one of these is going to be e to the x. So one of them is the exponential function, and one's the exponent. You've got a fraction, you've got sine, cosine, tangent. You've got a negate instruction, which would be like a -1. You've got a truncate. Truncate means if I have x dot xx, I just get rid of the decimal and it just becomes x. You've got a round, and that would be where I go to the anything 0.5 or higher goes up. Anything 0.49 or lower goes down. Ceiling, that means to round but always round up, and floor means to round but always round down. You've got an arc sine, arc cosine, and an arc tangent. So you've got all your trigonometric, all your exponential, your logarithmic functions. You've got some data conversions with truncates, roundings, ceilings, and floors. You've got a lot of math instructions available to you. And then you've got a calculate instruction. So we can kind of just get an idea of what we're looking at here. The calculate instruction, you can pick a data type, again, right here. Okay, so this is going to be a real. And in the calculate instruction, treat it kind of like a graphing calculator where you can set multiple instructions in at a time. In this particular case, whatever's stored in MD300 is going to work with whatever's stored in 3.14. It doesn't mean I'm adding them together. It doesn't mean I'm multiplying them. What it means is the output is going to get stored in MD308 of this expression. So you build an expression in here, an algorithm that you're going to use. So this in one, the asterisks, this means that I'm going to square whatever's in MD300. I'm going to take that result because it's in parentheses, and then I'm going to multiply it by whatever's in input 2. And then store that result in MD308. The expression can be whatever you want it to be, right? So if you had, y equals mx plus b, and you wanted to, you've got the equation for a line or something like that, or you've got, the equation for Fahrenheit to Celsius conversion you could build into here, kilograms to pounds, you could build that expression into here, and then you could input the data that you need, and then output the data that you want. Conversion instructions here. So sometimes we take a number like a real and we want to convert it to an integer. It's pretty easy to take an integer and convert it to a real. If you ever want to take an integer and convert it to a real, there's actually a convert instruction to do that. Here's how cool it is. Ready? The integer 7 as a real number becomes 7.0. The integer -11 becomes -11.0. So all they really do is tack on that 0.0 if you do a convert from integer to real. From real to integer, it's not quite so trivial, right? Because all integers are whole numbers. So really, to convert them to real just gives them a different gives them a different memory allocation and puts a point in there. But it's always going to be a 0.0 because it was a 0.0 to start with. But when we convert from a real number to an integer, so as an example, the number 3.7 stored in 1304, if I truncate the decimal, real to integer, and I truncate the decimal 3.7, that means I get rid of the decimal. So 3.7 becomes 3. I chop it off. If I take 3.7 and I want to go floor, think about what floor means, right? Floor means down here, and ceiling means way up high, right? What floor means is I take it down. Floor really means I want to round down. So 3.7 becomes 3. Ceiling means regardless of what this number is coming in, 3.7, but even if it's 3.1, ceiling means you always go up. So 3.1 into a ceiling instruction would become a 4. So these are not rounding instructions per se. One is to chop the decimal off, one is to always round low, one is to always round high, regardless. And then you do have a round instruction as well, right? Where if you had a round instruction and you had 3.4 coming in, you would end up with a 3 coming out. But if you had a 3.8 coming in, you would get a 4 out, right? These guys are not rounding instructions down here, okay? A normalized instruction. Oh, and I love this instruction. This instruction can be handy if you are dealing with a drive, a servo drive, a VFD or something, where they're expecting a number, let's say from 0 to 100% or something like that. A normalized instruction allows you to input a minimum and a maximum value. So my minimum is 100, my maximum is 0. So whatever is normally stored in MW34, and actually I feel like I got these backwards, like this should be 0 and this should be 100, right? The max should probably be bigger and the min should probably be smaller. But anyways, if I have a value coming in that's always between 0 and 100, what this will send out is it'll send out a number between 0 and 1.0. So if 50 is coming in right now, I'll get 0.5 coming out. And if 25 is coming in right now, I'll get 0.25 coming out. And that seems kind of trivial for 0 and 100, but it doesn't have to be 0 and 100. You could have a range of, 32 to 212. And now you can get where am I at in that range? Am I at 0%, 50%, 100% of that range? This is really the equation it's doing. It's taking your value in, subtracting out the minimum, and then dividing that by the maximum subtracted from the minimum to give you a percentage of the overall range. So in this case, I have a range of 180 between 32 and 212. Where am I at in that range? Am I halfway up that range? Am I down at the bottom of that range? 32 coming in should give me a 0 out because that's at the bottom of the range, right? And scale X. Scale X is also pretty cool in that I can use the scale instruction to scale the value at the value input by mapping it to a specified value. So in this particular case, I can take this value coming in and scale it to a new range coming out. And this takes a few steps here or there to make this work. But again, if you're trying to scale 0 to 100C to 32 to 212, the scale instruction can come in handy as well. And with that, I think that should prepare everyone for the basics of the math and compare instructions that you're going to see in the TIA Portal software when working with the Siemens S7 1200 PLC.